Okay, so our next talk is going to be given to us by Richard David, who's coming to us from Stockholm University, and it's going to be about some of the kerfuffle surrounding whether or not inflation is a scientific theory or not.
Thank you. Yeah, let me first thank the organizers, Kevin in particular, for this great conference and for inviting me. What I want to talk about today is the assessment of the theory of inflation. And I should emphasize from the start that I won't present any assessment there. Clearly, this is what physicists would do and should do. And for me, as a philosopher, I see the role of looking at the methods of assessing those theories and trying to understand the structure of those methods and maybe get something out of that. I think I don't need to say anything at this stage generally about inflation. Just mentioning that, in particular with respect to the Planck data, there has recently been some data that is understood to provide generic, so let's say to be in line with generic predictions of models of inflation. The situation is that the Planck announcement, and in agreement with many exponents of inflation, understood this, and I quote, as powerful evidence in favor of simple inflationary models. And a little later, there was a response to that in a way by, in a paper by E.S. Steinhardt and Loeb, where they argued to the contrary that actually this data generates substantial problems for inflation. And that's where a debate ensued between that ILS group, as I will call them, and a number of exponents of inflation who responded to that, and then there was a response back and so on. So let me just briefly sketch the way this exchange went. It started with this first paper where ILS just point out that the simplest, most straightforward models of inflations are ruled out by the data, and that slow roll single field models, which seem to be favored by the data, actually look fine-tuned. So that was their first claim. And to that there was a response by Guth, Kaiser, and Nakamura, where they first doubt the fine-tuning statement, which will be less relevant for us in this analysis. And second, they point out that that ILS use an overly confined understanding of what inflation amounts to. So they indicate that this single field inflation is by far not the only way one can and would want to construct inflationary models, and they suggest that actually more complicated models seem to be favored by some more fundamental theories, such as, in particular, string theory. To this, ILS then respond in another paper, and a little later then making this discussion public in a Scientific American article. And their main claim is that if inflation works the way Guth, Kaiser, and Nakamura claim, then there are no constraints on model building anymore in the inflationary framework. And therefore, basically everything could be reproduced, which means that it makes the theory untestable. So then they attribute to this the term postmodern inflation, which they use actually as a technical term. They distinguish this postmodern inflation from what they call classic inflation, which was what they take to be the initial inflationary paradigm. But of course, there is an intended attack involved in this on inflation, and the analogy, let's say the postmodern analogies, meaning that this retains the form of a scientific theory, but doesn't fulfill the function of a scientific theory anymore, are obviously intended. So to this, then there is a public response by Guth and 40 people who, exponents of inflation, who signed that response, where they very strongly, in very strong terms, reject that charge, and they emphasize that first, accommodation is a standard element of science that couldn't just be considered non-scientific. And then they emphasize also the point that one cannot claim total accommodation if conceptually preferred model classes were confirmed. So I would think that this dispute actually addresses an important issue in the context of understanding the status of inflation. And it also reflects quite deep philosophical differences regarding the mechanism of the scientific process between the exponents of that debate. And these differences have a lot to do with the distinction between model and theory in cosmology, and the question whether it is in a context where there are there's so much freedom to model building, whether it's enough to test models in order to confirm a theory. Now I want to highlight two elements a little more specifically of the ILS criticism in order to get a better understanding of what they are talking about and what they want to convey. The first element has nothing to do with the multiverse. It actually is independent of a multiverse assumption. The second I want to focus on is a specific point in their criticism of the multiverse. So if in this first case, if we just set aside the multiverse and consider a canonical relation between theory and model, this means that only one model, at most, would be actual, and all the others are not realized. And so the main claim of ILS is that even though there can be a bulk of typical models of inflation, a bulk of models of inflation that agree with the data and that physicists take to be typical, there can be models, if you get more complex, that match very different experimental data sets as well. And the theory of inflation, of course, does not attribute a priori probabilities to the models, in particular in this setting, which means that one cannot even exclude that unconceived models or new conceptual input, theoretical input from some side, could change our current understanding of what is generic in model building. Therefore, the theory itself, the theory of inflation, if you want to call it that, does not actually make any predictions. Predictions can only be established at the level of model specification, but it does not reach up to the level of theory in the end. Empirical confirmation of a model therefore doesn't amount to confirmation of the theory. In this sense, inflation as a theory is not empirically testable. So that would be their first point. Then they have another point that is related to the multiverse scenario and the problem of finding the correct measure in the multiverse scenario. And in the multiverse scenario, of course, we are in a situation where everything that is possible happens somewhere, which means that in order to understand probabilities there, in order to understand how probable a given outcome to us is, one needs a measure over the set of universes. And current physics does not enforce one specific measure of that kind. Actually, Guth and al. Feel confident with the situation, and they argue that in such a context, specifying the measure is actually part of the inquiry. So you apply a measure not in order to find out whether the theory is probably correct or not, but you apply the measure in order to find out whether the measure is correct. So if there is a problem, which happens to be the case in the most straightforward and simplest measure you could come up with, then you discard the measure for that reason. You don't discard the theory, but you look for different measures. And this is rejected again by ILS because they claim that this puts the hierarchy of theory testing upside down. So if you want to test a theory, you need to enter with a specific choice of measure in order to rely on measurement. Otherwise, you are not seriously testing the theory at all. So therefore, once again, they come to the conclusion that inflation, once it deploys these methods, has left the framework of genuine scientific reasoning, and we end up with this postmodern inflation. So, if one looks at the differences between ILS and Guth et al., they boil down to substantially different perspectives on the character of the scientific process. And it's probably fair to say that ILS have a traditional, one may say, empiricist, maybe Popperian view on that process. One aspect of this is that they de-emphasize the concept of confirmation. So they don't talk about confirmation of theories, they talk about testing theories, they're talking about favoring or disfavoring theories, but they don't talk explicitly about confirmation. Second is that they assume that a scientific theory ideally should be stable already once you start testing it. I know, of course, they don't claim that that has ever been the case with respect to inflation, but that's the ideal of empirical testing they have in their mind, and that's kind of the gauge against which one needs to assess whether empirical testing works or does not work. So this means that they have a step-by-step process in mind, where first the theory needs to be developed, then the theory's predictions need to be understood, then we test the theory, and then we confirm or reject the theory. So that would be their idea, and their understanding is that inflation needs to get as close as possible to this ideal scheme. Now, if one thinks about their distinction between, up there I wrote old and new inflation, which doesn't make sense, but between classic and postmodern inflation, the idea is that the classic inflation, that understands inflation as a theory, as single field inflation, not overly complex potential, and that's it, they understand this as testable. Because it is sufficiently close to that understanding, you can cover that theory empirically, you can understand whether models that are generated on that basis are in agreement with the data or not. If you then widen the spectrum of allowed models, they claim, you can basically do whatever you want, and therefore testing a model does not amount to testing the theory anymore. So the theory is not testable. Now, if one thinks about this argument, from the start there seems something strange about this. There seems something unsatisfactory, which has to do with their apparent understanding that defining what you call the theory and what you call a model or a group of models determines whether what you're doing is scientific or not. But it seems to be just a matter of terminology. So something seems to be strange here. And it turns out that one can pinpoint what is strange here if one applies to their concept the Bayesian framework of the Bayesian concept of theory confirmation. Now, as I've said before, they themselves don't endorse such a concept. They don't talk about the theory confirmation. But I would argue that applying the concept here demonstrates the merits of using a Bayesian framework for understanding theory testing and theory confirmation. Because once you apply the concept of Bayesian confirmation here, it becomes very clear what the problem is. And it becomes very clear that what they are doing is not just a little strange, but it's actually incoherent. And the point is that in Bayesian confirmation theory, you specify updating. I haven't written this here because I wanted to keep the graph here. But you specify updating as the posterior, so you specify the posterior probability of a hypothesis given the evidence in terms of the probability of the evidence given the hypothesis. And what enters then is also the prior of the hypothesis, of course. Now, if you think about a situation like that, where you just have this classic inflation that they claim to be testable, of course, the fact that this classic inflation is testable doesn't mean that the other options go away. They're just not part of that theory. Which means in the Bayesian context, that those theories and the probabilities you implicitly attribute to those theories are very relevant for assessing the prior probability of the hypothesis of the theory itself, prior probability of this. If you want to do that, you need to think about all this in order to understand, so given that the entire probability of all options needs to be 1, you need to know all this in order to understand what the prior is here. And you also need to know all this in order to understand the probability of the evidence given the theory. Because if there are many other theories back there that would also be in agreement with the first data, then that means that it lowers the probability of the evidence given the theory, right? Because they're, once again, the same argument. Which means that if you're in a situation where theory building after that, after the first evidence, is so flexible that you can still reproduce after the first evidence basically everything you want, then this will dramatically reduce the prior probability of the hypothesis, and it will also make very small the probability of the evidence given the hypothesis. So this means that from a Bayesian perspective, it's completely irrelevant whether you take this to be the theory or take that to be the theory, because in terms of probabilistic assessment, in principle you do the same thing. Either you can test the theory or you cannot. In other words, the way they present it, if there is a problem for inflation, it's not just for postmodern inflation, but it's exactly the same problem for classic inflation. The one thing they would need to do in order to avoid this is they would need to reduce the probability of those other options by hand. So that if they say, we now declare the probability that anything else happens is next to 0, then they have confirmation. But this, of course, doesn't make sense. In particular, it doesn't make sense from their empiricist perspective because they have no basis for doing so. So what one can learn from this, however, is that given that there is a problem of model proliferation, what one needs in order to control this, and what one needs in order to turn this into a testable theory, is some information about that goes beyond the theory itself. So some information that assesses the overall theoretical framework. Now, and they don't address this, of course. So my point with regard to ILS would be, first, it's just false that classic inflation fares any better than postmodern inflation. Second, if there is a problem, in order to deal with that problem, one needs to do something that they don't want to do. So their empiricist perspective prevents them from reaching out beyond assessing the theory itself. Now, if we move on to the Guth et al. Perspective, let's say the majority perspective among inflationary cosmologists probably, they have a far more flexible view of what the process is, right? So they understand that the theory itself is a theory in flux that develops based on theoretical input. So for example, if one thinks about a string theoretical fundamental theory that determines the layout of inflation, then the more one understands about string theory, the more understands about the connection between the two, the more one understands about the specific constraints on inflation. So that would be those arrows here. And you also can have a situation here where actually your understanding of the testing process evolves or develops based on a better conceptual understanding. So that would refer, for example, to a choice of measures and motivation of measures based on, for example, on fundamental theory building. So this seems to be, clearly it's a more processual view of the scientific evolution, and it seems to reflect the situation of fundamental physics today much more adequately than the old picture. I mean, that seems to be the situation most of fundamental theory, quantum gravity, string theory, inflation, finds itself in. However, the initial problem ILS point to remains. The question is whether the selection of a model class and the demonstration of reliability of the testing process can be postponed ad infinitum without compromising the scientific method. And it's not clear how to handle that just based on acknowledging that there is this processual process, that there is this processual understanding of developing and testing a theory. So one seems to need something else, and on the prior slides I already indicated what I would think that should be in order to understand how, on what basis one can have trust in the theory of inflation. And what one would need is reasons to have trust in the theory of inflation already during that process. And reasons that is not just based on evidence itself, but it's based on evidence about the entire framework of scientific reasoning we find ourselves in. Now, this seems quite consistent with the actual perspective on string theory on inflation many exponents of inflation have. So it seems clear that there is a considerable degree of trust in inflation among many theorists. And it is understood by those exponents that there are actually substantial reasoning for having that trust. And I just give you this one quote by Andre Linde to demonstrate that people can be quite explicit about this. Now, what is interesting about the response by Guth et al. To the ILS criticism is that this response does not strongly emphasize the trust in inflation. So they do not, in their papers and in their later response in Scientific American, they do not strongly establish that data confirms the theory of inflation rather than specific models. They rather focus on the fact that already if you test models, that's what scientists do. So that's sufficient. But what I try to indicate is that it's not really sufficient in situations where there is a huge proliferation of models and where you might question how significant that confirmation can be with respect to a research program or with respect to a theory. So there may be 2 or probably 3 reasons for this. First, they are very directly responding to ILS, so they respond immediately to the immediate charge ILS make. And second, there is probably not much interest in engaging in what they would understood as philosophical discussions about trust in the theory. And it might also be that among those 40 signers of the paper, not everyone had the same perspective on the degree of trust one might have. Still, I would argue that in order to have a consistent understanding of the basis for testing, significantly testing the theory of inflation, one needs to address that issue. So I think one needs to address that issue for 2 reasons, actually. First, in order to actually represent the position many exponents of inflation have with respect to their theory. And second, in order to give a full-fledged answer to ILS. So what would be the basis for a more ambitious defense? And what I claim, maybe not surprisingly, is that it would rely on meta-empirical theory assessment, so a specific form of non-empirical theory assessment. How much time do I have actually?
About 16 minutes.
16?
Sorry, no, 16 till the 5 minute.
Sorry? Okay, 20 minutes. 20 minutes.
Including questions.
Yeah.
Yeah.
All right, so I did the math now and...
Can I ask a quick question? Can I ask a quick question?
Yeah,
What do you mean by meta-empirical theory?
I will explain that right now. Yeah. So the idea is the following. The idea is that we have empirical theory confirmation that clearly in a Bayesian, seen from a Bayesian viewpoint, increases the credence for a theory's viability based on empirical data that is predicted by the theory. So that's straightforward. Though I may not have the time to point that out in detail, I would argue that empirical confirmation always needs to be supported by non-empirical or meta-empirical confirmation in order to understand its significance, its relevance. And to a certain extent, one can understand it quite well from that perspective, because in this case, we do have a situation where clearly formally there is empirical testing, but the question is whether it's significant. And we need non-empirical, meta-empirical methods in order to establish that. So this would be the first form of confirmation, and the second form of confirmation would be what I call non-empirical confirmation, which increases the credence in the theory's viability based on some other types of evidence. So evidence that is not in the intended domain of the theory, so it's not of the kind that can be predicted by the theory. So more recently, so since non-empirical theory confirmation may cover lots of things, recently I've come to specify the 3, in my understanding, most important forms of non-empirical theory confirmation, to characterize them with a specific name, which is meta-empirical theory confirmation. And I define this as confirmation that provides increased credence on a theory's viability based on observations that are beyond the theory's intended domain, but that allow inferences on the spectrum of unconceived alternatives. So those are strategies that evidence that we extract from the research process, and evidence of a kind that can specify, that can determine or can indicate better on let's say, provide us some message about the spectrum of unconceived alternatives, of possible alternatives to the theory at hand. So the reason why this works, in my understanding, better, substantially better than other strategies of non-empirical confirmation is that it is formally quite similar to empirical confirmation. So while in empirical confirmation you have this relation between theory and empirical data, the theory predicts the data and the data, if an agreement provides empirical confirmation, in a pure case of meta-empirical confirmation, there is no empirical confirmation. There is no empirical data. But what you might have is a hypothesis on the spectrum of alternatives. So you say, for example, in the most extreme case, the hypothesis is there are no possible alternatives, scientific alternatives to the theory I have. So, of course, one needs to spell out the details, what I mean by scientific theory and so on. I don't have the time here to do that. But let's say that makes sense. Then this hypothesis would predict meter-level observations. And if I find those, the agreement between this meter-level observation and the prediction then kind of empirically confirms the meter-level hypothesis, which of course altogether is not a rigidly scientific process at all. It just has the form of scientific confirmation in a much more loose and much more vague sense. And now if I then increase the probability of the hypothesis, this hypothesis will then increase the probability of the theory. So in this extreme case, if the hypothesis is there are no other possible theories than the one I have, if that's the case, and if I assume that there is a scientific explanation, a viable scientific theory, then I can infer that that's actually the correct theory. Now, there are three main kinds of meta-empirical confirmation. The one we will be focusing on here will be the very first one, the most straightforward one, which is the no alternatives argument, which is just based on the observation that one doesn't find alternatives to the theory, which on its own is not a very powerful argument because one might just not find it because one is not clever enough to find them. But it can turn into a significant argument based on a second argument, the meta-inductive argument, which makes the observation that other comparable theories in the research field were that shared some characteristics, for example, that shared an alternatives observation initially, before it having been empirically tested, then got empirically confirmed once they were testable. And then there is a third argument, unexpected explanation, which is based on, once again, on an observation at the meta level, which is the observation that the theory was developed in order to explain something, and then ended up explaining other things it was not developed for. Then I might add that those three arguments are those arguments that already work, that can play a role even in the absence of empirical confirmation. So for example, in a case like string theory, they can already play a role. There is a fourth argument that is actually fairly well known and that fits very nicely in that framework, which is novel confirmation. So if we look at novel confirmation, is based on the observation that the theory predicts data that had not entered the construction process. So it is the opposite of accommodation. And in this framework, in the framework of assessing the spectrum of alternatives, novel confirmation, as opposed to accommodation, also gives an indication of the limitations to the spectrum of alternatives. Because if I have lots of alternatives, in this particular case, they may make different predictions, and I don't have no basis for assuming that the predictions of the theory I have developed are actually correct. So, so that's the idea. And the important point of this, or the crucial point, is that just based on assessing the research context and based on evaluating what is going on in the field, can provide a certain extent of understanding of the spectrum of possibilities, which of course is something that I, at first glance, one think is just not possible. And clearly, from a strictly empiricist point of view, one would think one would have the position that this is not something you can do, because you don't know anything. How should you know anything about theories you haven't thought about yet? And the idea is that this methodology actually gives you, to a certain extent, a handle on that. And the second crucial point is that this is not just hypothetical, but is actually a crucial element of scientific reasoning in general. And in particular, it becomes particularly important in cases where either there is no empirical confirmation, and there are reasons to apply those methods, or also contexts where there is empirical confirmation. There is a lot of empirical data, but the relation between the data and the theory is very complicated. And of course, that is, for this, inflation would be a classical example. So let's see why this meta-empirical confirmation works better than the ground level when assessing the theory. And the core point here is that these meta-level arguments by nature address the theory level and not the model level. So if I assume I think I have an alternatives argument, in a case like inflation, clearly that alternatives argument will not play out at the level of models, because I know there are lots of models. It will only play out at the level of theory. So I directly address this level of reasoning, where I want to establish confirmation. And now if I do that, and if I am in a situation where there is no clear-cut no alternatives claim to be had at this point, and I try to apply an alternatives argument, I can interpret incoming data in a different way, because new incoming data has the potential of ruling out alternatives to the hypothesis. So if in this particular case I have inflation and I have alternative approaches, and I gather additional data that has the potential either to rule out inflation, but if inflation is as flexible as Steinhardt et al. Claim, then that won't be awfully likely. In other understandings, it might actually be possible. But that's one option. The other option is that it rules out one of the competitors. And in ruling out the competitors, so this happens at the level of theory assessment and not at the level of model assessment. And in this particular case, the one model I can find that is consistent with the data is already crucially relevant for that step of analysis. I don't need to ask how many other models are there. If I have one, I say, okay, the theory has survived this. And if in another case I have none, the theory is out. And this, of course, if that theory had a substantial prior probability, if that theory is out, it boosts the probability of the alternative theory. So on that basis, I get empirical confirmation in a sense, based on those non-empirical reasoning. So I don't get I don't see the empirical confirmation if I just look at the context of the inflationary theory itself. I only see it if I look at the context of possible alternatives. So, and once again, of course, there are exponents of inflation who make these kinds of arguments with respect to inflation already at this point. So it is an argument that is under consideration, let's say, in the given context. Now, I will be very brief about other possible contexts, and with respect to unexpected explanation, I just want to mention one example of unexpected explanation, which is anthropic reasoning. So if you look at anthropic reasoning as an explanation of the functioning of the cosmological constant, then this clearly is an unexpected explanation you get out from string theory. So clearly no one, when developing string theory, had that in mind when they tried to develop the theory. It is just one example, though it's not awfully strong. My feeling is that the unexpected explanation case in the context of inflation is not as strong as in other for other theories. But I think they can be found. I mean, one might also, if one looks at the detail of the history, one might find in the very early stages of inflation instantiations of that as well. Now, coming to novel confirmation, we need to address one point that is not sufficiently covered by focusing on this meta-empirical explanation confirmation issue. In order to have novel confirmation, of course, one would need to take seriously generic predictions of the theory. Yeah.
Sorry, can you go back to the previous slide?
Yeah.
So I understood that the unexpected explanation argument to refer to the case in which a given theory for which we may not have a direct empirical confirmation manages unexpectedly to explain another empirically confirmed fact. But you seem to be using it here as simply having provided another context in which another type of explanation is needed. A type of explanation based on anthropic reasoning is needed. It has nothing to do with the cosmological constant per se being now measured, or any other empirical fact that is unexpectedly discovered.
Well, if you focus on new data, that would be novel confirmation, right? So if the theory predicts something, and then you collect data that is in agreement with that prediction, that would be novel confirmation. The unexpected explanation case would be, let's say, at a more conceptual level, and this can play out in several respects, I think. And one of the respects I feel is this one, right? So whether or not the measurement of the cosmological constant has happened before or after the theory, what makes this not, it's not a good case of of novel confirmation because it's not sufficiently strong as a prediction, right? I mean, there is this very weak predictive element there, but you would not want to take that predictive power of predicting the cosmological constant itself as a strong case of novel confirmation. It seems to be more plausible to frame it in terms of unexpected explanation. So this is not as strong as novel confirmation. Right? So you may say that this particular case of a fine-tuned cosmological constant can be explained by anthropic reasoning, in the sense that it's not too far off to indicate that this cannot be the only explanation.
No, I understand, but the unexpected explanatory argument, again, maybe I'm just misunderstanding, but my understanding was that it works like, okay, the theory is designed to explain a certain set of phenomena, and unexpectedly manages to explain a totally different set of phenomena.
Right.
Whether empirically confirmed or not.
Yeah.
But what is it that it has explained, with the inflation has explained that was unexpected?
So
Not designed to explain. What is the new aspect of the world?
So the new aspect of the world is the fine-tuning of the cosmological constant. And the explanation goes starting from the inflationary perspective, goes via the anthropic argument. So it goes via the multiverse, via the anthropic reasoning that can play out in this context.
Actually, I don't quite understand that it would be nothing bad if the present small anthropical constant would be 0. So in this sense, so it should not be too large. And actually, in my talk, I just presented you this condition, which includes not only the cosmological constant, but all other four fundamental cosmological parameters. So the most important is the relation between amplitude of initial perturbations and the present cosmological constant. But once more, it's that this condition is an equality. So I would say that at least from naive point of view, it would be nothing bad if it would like cannot nature be absent at all.
Right. Yeah. I mean, this also. I mean, it's not the claim that anthropic reasoning explains the necessity of the cosmological constant. The claim is, given that so it is. I would agree that this particular case is kind of placed in between a novel confirmation argument and an unexpected explanation argument. I would rather categorize it as unexpected explanation because as a novel confirmation argument, it is not awfully impressive, right? It is not a precise prediction whatsoever. But one may place it in between the two, and I think there is a continuum between those two. So yeah, just to conclude, I'm close to the conclusion already. The question that remains here is why it's not clearly this meta-empirical reasoning is not the only basis for exponents of the theory would present as arguments in favor of the theory. So they would quite strongly emphasize the generic character of the predictions, pointing at a specific class of models. And this meta-empirical perspective on this has not much to say about that. So one would need to enter a different kind of discussion to understand why this notion of genericity actually makes sense, even though there is no full understanding of the spectrum of models, full understanding of future theoretical input that might change the understanding of what is generic. One probably might frame it in a similar way. One might say that this is based on some assessment of the perspectives people have, but it's not. I think it's not possible to support that by meta-empirical evidence, as it's said. At least to me, it's not clear how one should do that. So I would want to emphasize that this meta-empirical aspect, I think, adds something to the picture, but it is not in itself sufficient for understanding the trust in the theory inflationary cosmologists have at this point. So the conclusion is that if one takes postmodern in the sense of criticizing the theory, I think it's not an adequate criticism per se. I think that there is a methodology based on which one can assess the theory. And as I've said, I myself do not want to evaluate the position of individual exponents of the theory, whether more or less trust is correct. All I say is that there is a method of carrying out that is rational. However, I would want to point out that this method actually goes beyond a straightforward empiricist point of view on theory testing. And I think that ILS are right that once you decide to endorse such a strictly empiricist perspective, there is exactly the problem they identify. Thank you.
Thanks very much for the lovely talk, Richard. Just a really quick question, and I think you'd probably be able to predict what question I'm going to ask. But what is you need the on your view you need the meta-inductive argument to ensure significance for the no-alternatives argument. What is the inductive base for the meta-inductive argument in the case of inflationary cosmology?
Yeah, that's a good question. Of course, the meta-inductive argument is a very flexible argument, right? So you can trace it back to a number of contexts, I feel. In the case of inflation, there is a vicinity to analysis in high energy physics. So I think that success stories in high energy physics definitely contribute. Probably they play the strongest role.
Chris, thanks.
So I want to raise a general worry I have about the no alternatives argument. And I think it's nicely illustrated in this case, which is that I think it's hard to make that argument without making a substantive commitment about the form of the theory that you're aiming for, and that's often contentious. So in this case, there's a question. So there were puzzles about standard Big Bang cosmology that were recognized in the 70s. Starobinsky and Guth and others introduced inflationary models that were quite successful. And that leads to a way of linking different properties of the early universe that for a while were seen as any theory worth its, any early universe theory had to similarly link those problems and solve them. But we've seen in Robert's discussion that there's a different way of understanding what a criteria for successful early universe theory are now, which is really a causal mechanism for generating an appropriate perturbation spectrum. And depending on which of those views you take, if you say a successful early universe theory has to link the horizon structure, the flatness, and the perturbation spectrum in a particular way, or is it really just responsible for giving us a causal account of the perturbations? What you count as an alternative will be different depending on which of those you take as the definition of what a successful theory is. So I would imagine that Linde probably had something more like the former account of what a theory should be, whereas if we go with Robert's criteria, then that opens up a space of alternative theories. So I think it's hard to remain completely agnostic about the substantive questions about what a theory in this domain should be doing in order to formulate the no alternatives argument.
Yeah, I mean, I think I would view, I mean, in principle, I agree that this is an issue, and it's a difficult issue. In the particular case, I would view the situation slightly differently, I think. I would say that the process has been, that there has been a development towards a more integrated understanding of cosmological theories. One demands more from them. I don't think that the current understanding drops substantial aspects of what was the initial motivation of inflation. Maybe the monopole issue, but apart from that. But it requires more than that nowadays, right? So clearly there is a stronger emphasis on the theory being consistent with the fundamental theory, for example. And lack of compatibility with string theory, if that arises nowadays, would be a very serious problem for a theory. Maybe not fully rule out the theory, but it would be considered by many to be a very serious problem. There may be other issues there. So I think there is a movement, a development towards a wider assessment of the theory's merits and also potential disqualification. But that, I think, is not problematic, but rather the opposite. I feel that the wider that spectrum gets, the more difficult it is for a theory to survive, and the more promising it actually is to look for no alternatives cases.
Okay, then first I would like to actually say that, as I said in my talk, the most simplest models of inflation, which are sufficient to explain existing observational data. I had no time to discuss all possible extensions, when they actually only one parameter. So that's why I would say what I'm against using double standards. For example, what is the contract extension of a standard model elementary particle? Okay, many it's not three people consider one model by another. Many models are excluded, okay, we don't know. But still we are sure that the standard model is not the final one. Okay, once more, that's a way we have essentially the same situation with inflationary model. As I said, at present, one parametric model, like my model over Higgs are sufficient, but okay, they make definite prediction. They make definite predictions, so that they in future will be falsified or confirmed about the amount of gravitational waves. Or okay, then in this case nothing bad occurs. It is similar to the initial hypothesis of Pauli of the existence of one type of neutrino. When it appears that there exists a second type, third type, now the possibility of stereo neutrino is considered. So that's why I would say I would prefer to speak about models. So models at the present level of understanding, one parametric models are sufficient, but I had no time to set it. It may well appear that we need to introduce more complicated model, and one of the most, I would, straightforward possibility if we really discover primordial black holes with mass characteristics for the solar mass. But it will be a new discovery, okay?
Yeah, I might say two things about that. First, the way I understand it, I mean, clearly testing models is important and very helpful. And as I said, it doesn't. In principle, it's not where one draws the line towards characterizing something as a theory is not essential for the effectiveness of testing. However, I think that it is helpful to talk about theories in exactly in those contexts where one tries to make an alternative claim. So in order to make such a claim, one needs to go to the highest level possible, so to say, because there it is more likely to find one. And that, I feel, is the one reason why it is nevertheless helpful to think in terms of theories. With respect to models and comparing the situation, the standard model situation with the situation in cosmology, I might point out one aspect of the way I understand these issues of meta-empirical confirmation. It is always helpful in order to find any cases of no alternatives or of meta-inductive arguments to be able to find some empirical horizon for the theory. So in a standard model in a high energy physics context, this means to talk about effective theories up to a certain energy scale. And if one wants to decide whether, let's say, the standard model is likely to be valid up to a certain energy scale, obviously that's a very different question from the question whether it is valid up to the Planck scale. So I may say, okay, sure, if I go up to the Planck scale, I have no idea. So the standard model is drowned in, or is drowned in possible alternatives. But that's not very significant, because I still can be confident about the electroweak scale. If something similar arises in the context of cosmology, I would also agree that it's not that relevant to look at higher energy scale models, let's say, if I can decouple them from the low energy scale. So the proliferation of model is only such a big problem if I cannot do that. If I cannot say that this is for another energy scale, so I'm not interested in that at this point. I'm interested in the effective theory.
I'm very sorry, we don't have any more time for questions, because we went into the question period a little bit because there was discussion during the lecture. So let's thank our speaker one more time.